Here we go. Well, take a look at my sheet that I made for you. Okay, here it is. Whoops. There we go. All right. Now, tell me if this makes sense to you, okay? Because I'm going to be honest with you. I feel pretty certain I did not understand the mole concept in high school. I'm going to be even more honest with you. I don't think I actually understood the whole concept in college. Now, I was able to struggle through my way through some of this stuff, but it would have been a whole lot easier if I'd understand the concept of it. And here's what I thought. I thought this chapter on stoichiometry, even in college, it was like, wow, there's like 12 kinds of problems. And I better remember how to do all 12 kinds of problems. And yet, there was a common link. I found out later, there's a common link. If I understood some of these concepts, it's not really 12 different problems. They're very similar. I just have to do this, take one step, and all of a sudden it's just like the other problem. And so I don't need you to learn 12 different kinds of problems. It's kind of the same idea. So stay with me a little bit, and we'll spend a tiny bit of time on this, and you tell me if it makes sense to you, all right? Now, we did this the other day. If you're going to do factor label, and that's a powerful thinking tool. It's powerful, but you need equivalence, don't you? Yeah. Now, we did this. If you're an element, I want you to review this and then fill this out. Fill this one out for barium. Here it is for sodium. Here it is for uranium. Everybody get a pencil or a pen out. Go ahead and fill out for barium, and if you get this correct, we'll move on. And we'll keep moving on. I have examples for each one. And every time you get it right, you'll say, I think you got it. Does anybody want to just volunteer and say, I feel pretty confident about this one. I think I can do it.
This one?
Yeah, you want to do it? All right, Jeff, ready.
So a mole is 6.02 times 10 to the 23rd. And then
Wait a minute now. I need some labels.
the label is going to be atoms
Why?
of barium.
Why?
Because 1 mole is a ton of atoms.
Yeah, but
So,
it could be a ton of donuts.
Okay.
So what you're thinking is, what's the smallest piece of an element that still has the properties of the element? Atom. Okay, keep going.
And that's going to turn into 137 grams of barium.
Why not 38?
And where'd you get that number?
There.
Okay, they're okay?
I've been allowed to have everything.
Oh, okay.
Yeah, it actually looks.
That'll make your life a little easier.
This salsa is so spicy.
What is?
The salsa.
You're
Yeah.
gonna sell their company.
Can I do it? No.
Is it not the mild that we're ordering?
Jeffrey, you're getting tired. Your boss already
You're
knows.
playing tonight.
You went in there, we all thought you were doing great.
So he's
It's gonna be like, it's not spicy at all.
Yeah.
You sure did.
Okay, hold on. All right, so if you look on the periodic table, one of the numbers you might see there, it says 137.3, and I don't care if you use 137.3, that's fine. But that is how many grams it would take to make a mole of barium. So if I gave you 137 grams of barium, I would know that there would be 6.02 times 10 to the 23rd atoms of barium sitting in front of me. And what's the special name given for the amount of grams, the mass that it takes to make a mole? What's that called?
Avogadro's number.
Avogadro number is the number of particles.
Molar mass.
It's
I
the
think it's
number of
called molar
particles.
mass.
Okay. Right here,
No, atomic.
right here, right here.
There, there.
I'm ahead of you. Okay.
Because it was right there.
So it's called molar mass. Everybody got that? That's how many grams it takes to make a mole. Now, Avogadro's number is the number of particles it takes to make a mole. All right, but they could have different masses, couldn't they? All right, let's do number 2. What if it's a covalent compound? That means a non-metal compound. Somebody volunteer for that one.
I got it.
All right, go.
So you got 6.02.
And this is glucose.
You got 6.02 times 10 to the 23rd molecules of glucose, which is equal to.
Why do you say molecules?
Because it's not atoms, it's a compound.
Okay.
Because it's the
And it's
smallest-
the smallest part of a covalent compound that acts like that is a molecule. Go ahead.
And then so you're gonna have, so C, the molar mass of carbon is 12, so you times that by 6, and that's 72.
Okay, 72.
Plus you have 12 hydrogens, so 74, 84, plus O times 6, 84 plus 16, 6 times.
Uh-huh.
I think it's 16.
And I'll give you a clue, 2 times 16 is 32, so 32, 32, 32.
Yeah, 96.
Okay, 96, so 96 and 84, is that what it is?
Yeah, so that's going to be 180.
That's it. 180 grams, right? And that's called the molar mass for glucose. Okay, let's do another one. Ionic compound. Who wants to do that one?
I got this.
All right, Clay.
Well, first, what I would do is distribute, first would be, like I say, 6.02 times 10 to the 23 formula units of that.
Okay, and what is that?
Do you have it, name it?
Yeah.
That is a copper, is it one charge or two charge?
What do you think?
One.
What do you think? You had a 50-50 chance, didn't you?
Yeah.
Acetate's -1, but there are 2 of them. That means there's -2. This must be what?
So it's copper two.
Yeah. What's another name for copper 2 acetate?
So.
Wait, what's the other name? What's the other name for copper 2 acetate?
Is it cupric, or what are the charges?
It's either 1 and 2. 1 and 2.
So it's cupric.
It is cupric acetate. All right, next.
Uh,
Now, how in the world do you do this one now? How do you find the molar mass for this guy?
Oh, well, first I distribute that 2.
Okay.
To each of the individual atoms.
Okay.
Of acetate. So the 2 becomes a 4.
Okay, so if you have a calculator, you could try this. So how many coppers?
1.
How many carbons?
2. Oh, wow.
All right, 4. How many
4,
hydrogens?
6, 4.
6,
And how many oxygens?
4.
Okay. All right, so you put that in your calculator, and I don't know this one. I knew glucose because I've done that before, but does anybody have this calculated yet? Okay. All right. Anybody have it?
Copper is what, 60?
You're going to have a little trouble doing your head, but
63.5.
63.5.
Plus
122 maybe?
Seems like it'd be a little higher than that, but let me see. Well, copper 60, around 63, 64, and then 4 of those would be 4 times 12. That's 48. We're getting up there.
Oh, yeah.
And then that's going to be a little higher than that.
We're not trusting you.
Does anybody have it?
32, 64.
It's around
64,
190, right?
64 plus 6, that is.
So 60, it's 63.5. Okay.
70 plus 63.5.
Plus
is
48.
13.
That's 48. What is it?
181.5.
Pretty good.
Very good. Now,
Yeah.
that room there. All right, so anyway, that's the basic idea of how to make equivalents if you're going to do factor label. That's the basic idea. Now, there's something else I want to show you, and I'm going to go way back up here, and it's a little thing that we almost missed here. And this is from 2 years ago. But the people who developed the mole concept, almost every one of their experiments were done with gases. And they had a certain volume of gas, and they noticed 2 of those volumes of gases reacted with 3 of those volumes, or vice versa, something like that. And they came up with an idea. Avogadro said, equal volumes of gases at the same temperature and pressure, they have the same number of particles. That means that if you had a box and you put helium in it, and it filled this box, okay, at the same temperature and pressure, and you could count the particles, and then put another gas in there and count the particles, and they would have the same number of particles. Now, how big of a box would it take before that number of particles was a mole? Does anybody know what is the molar, not molar mass,
Is
what's
it a
the
liter?
molar volume?
Is it a liter or 22.4 liters?
Very good. How do you remember that?
Because I saw it at the corner of my eye.
Okay, good. So anyway, so you now can enter another equivalent if it's a gas. If it's a gas at STP, ST means standard. Let's pick a standard. They pick 0 degrees, 1 atmosphere of pressure. Now, you guys had physics, so 1 atmosphere of pressure, if I was at sea level, the amount of pressure is on me at sea level is called 1 atmosphere. Remember that? Or 101.3 kilopascals, you don't remember that probably. But easy to say 1 atmosphere, isn't it? Anyway, that was their standard temperature and pressure. And if you had that box right there, and that box is 22.4 liters, and you had STP, fill it with helium, there'd be 6.02 times 10 to the 23rd particles. Fill it with carbon dioxide, there'd be 6.02 times 10 to the 23rd molecules. And that was a big breakthrough in the mole concept. All right, one more thing down here on this side. Yes?
So, for example, like in a helium balloon versus a balloon filled with air, the balloon filled with air has the same number of particles as the balloon filled with helium.
If they're at the
Helium
same
atoms-
temperature and the same pressure.
Yeah, but the helium atoms are way less per individual atom. So
Right,
that's
but
why-
at that temperature, the lighter things are bouncing around faster, and they actually there's a little bit more space in between them. So that's a good question. Why would there be the same number of particles? I don't want to get into too much into physics, but kinetic energy is 1/2 mv squared. See that? The average kinetic energy is your temperature. So if these two balloons were at the same temperature, the particles inside them would have about the same average kinetic energy. But what if some of the particles had a tiny mass? If they have a small mass, they better have a bigger what? Velocity. What if you have a big mass? You'd have a smaller velocity. So it still comes out to be the same number of particles. That's an excellent insight. What you had there, okay? So you think they'd be bouncing around the same speed? They wouldn't be. The light ones are bouncing around faster, and there is a little more space between them. And the big guys have less space between them, but they're kind of moving a little slower too. Excellent thinking. Down here, this is something the book doesn't stress for whatever reason, but if someone ever asks you about how many grams is an AMU, let's just pretend. You say, am I supposed to memorize that? You could, or you could think your way through it. Look at this right here. I know that 1 mole of hydrogen is this many atoms of hydrogen, and I know it's about 1 gram. Is that correct? So I also know that 1 gram of hydrogen divided by the number of atoms tells me how many grams would a hydrogen atom be? Does everybody look what I did here? I took 1, divided by Avogadro's number, and I got this. So if you want to know how heavy a hydrogen atom is, it's that 1.66 times 10 to the minus 24 grams. And I didn't memorize it. I just used my concept. Now let's take it a step further. How much is 1 atom? 1 atom, not a mole of atoms. What does 1 atom of hydrogen weigh? Remember that? It has 1 proton? 1 AMU. So guess what? Then I can replace this. I can say then it's 1.66 times 10 to the negative 24 grams per AMU. Everybody got that? Because you said 1 atom has this weight, and that's 1 AMU. So what is an AMU? 1.66 times 10 to the minus 24 grams. So you don't have to memorize it. You could actually come back and rethink about, use hydrogen as your example there. The next thing I'm going to show you on the back, this is also a mole concept, and I know I was weak at this. I know that no one taught this to me. I know that when we start the next chapter, some of you are going to be weak here. And I'd like you not to be weak. And let's look at this right here. Let's do the mole concept. And I know in 10th grade you didn't like this, but what world are you in? Now, here we go. When I see a capital C, if I'm in the tiny world, watch now, if I'm in the tiny world, capital C means what? 1 atom of carbon. It also means 12 AMUs, doesn't it? 1 atom of carbon is 12 AMUs. But if I'm in the big world where they do experiments, what does the symbol capital C stand for in a balanced equation? A mole. And therefore, it would not be 12 AMUs, but what? 12 grams. Okay, you see how that works? So the mole concept took what was happening in the little world and magnified it so we can actually use grams. And that number up there means 2 things, doesn't it? How many AMUs 1 atom is, and how many grams it takes to make a whole mole. That's what that decimal number is up there. Now, let's try you try one, okay? And I know 3 of you volunteered already, so let's have the other 3, some more people do it. So who wants to volunteer for this one? Thank you. All right, go ahead. What does this mean in the little world?
1 atom,
Yes? Which would equal how much?
14 A.
How much?
Oh, sorry, I was looking at nitrogen.
Yeah.
23 if you round.
23 AMUs, right?
Yeah.
There you go. And that's called the atomic mass. The atomic mass. The atomic mass for sodium is 23 AMUs. Now go over here. In the big world, what's this? Yeah.
1 mole of sodium equals 23 grams.
It equals 23 what? Grams of sodium. And that's the molar mass, right? Not atomic mass, but molar mass. All right, let's do the next one. Let's go with covalent compounds. Now be careful in this one, it gets a little more complicated. If I think of this in the little world that I can't visit, what does H2O stand for? Who wants to try this one? Need a volunteer. You ready?
Sure.
Your brain, yeah, go. What does this mean in the little world?
1 molecule.
Yes,
And then it's 6 carbon atoms.
okay, so what? It's 6 carbon atoms,
12 hydrogen atoms.
And-
6 oxygen atoms.
okay?
And that will be, what's this?
180.
180. Yeah.
180 what?
180 AMUs.
Yes. What do you think? All right, take me over here, Clayton. Here we go.
Here, we'll have 1 mole of glucose equals 6 moles of carbon
Yes.
atoms.
Yes, 6 what?
6 moles of carbon atoms.
Yes.
12 moles of hydrogen atoms and 6 moles of oxygen atoms.
Wait a minute, you're ahead of me. What else does it equal?
And then that equals 180 grams.
Yes.
Of glucose.
Yes, and that's the molar mass, isn't it? This is the molecular mass, right? This is atomic mass, molecular mass. What's these? What are these? What's that? What's this? Molar mass. Okay, how about that? You think this? You got this? Okay, let's do the next one. Who wants to stretch and who hasn't done one yet? It's either be Marie, Parker, or Mason. Which one? Who's in
Well, I know I'm so smart, but I think I'll let Marie take the reins on this one.
Okay.
I did one.
All right. Marie, he's very nice. He's letting you do it.
Okay.
Such a nice one.
Such a nice lad.
So for this one, start off with 1 molecule, or sorry, 1 formula,
Okay, because ionic, isn't it? How do you know it's ionic?
because it's
You know something I don't think I've mentioned yet, but almost every polyatomic ion you had to learn. Did you understand that it's actually held together with covalent bonds, but it's overall, it has a charge?
Yes.
So it's called an ion, isn't it? A polyatomic ion.
Yeah.
It's actually held together with covalent bonds, and yet it acts like an ion, so what kind of a compound is this? Yes. Here's a +1 ion, here's a -2 ion, isn't that right? Okay, go ahead. 1 formula unit of this equals how many?
so you have 2 nitrogen.
We could do nitrogens, but let's do this ions.
Okay, so 2 ammonia,
Okay? And
and then 1 carbon.
carbonate, yeah?
Yeah.
Okay? And I don't know this one, but let's see if we can, let's help out a little bit, okay? 2 times nitrogen is 28, plus 8, that's 36. 36 and 12, 48. What's 48 and 48? That's 96. Is that right? Is that 96? Okay. 96 what?
AMUs.
Yes? Okay, now come over here.
And then, so that's gonna be
of ammonium, what's this called again? Ammonium what?
Carbonate.
Ammonium carbonate equals,
So 2 moles
yes,
of ammonium,
yes,
and then, or 1 mole of carbonate. And then 96 grams.
Now, what do you think about this? I think the students, if I could have been pretty solid on this, I know I would have understood chemistry a lot better in college. And it wasn't really till later that I figured out some of the holes that I had in my thinking. When I started teaching it, it's like all of a sudden I said, wait, I need to know this. If I had known this, you know, and that's what I'm trying to do for you. I'm trying to say, I want you to, when you go to college, be good at stoichiometry, good at mole concept. Okay, so what do you think about that so far? Yes?
Yes.
Okay. So now, what I'd like you to do is the handout sheet that I gave you, the little packet I gave you. Let me see if I can find mine. Oh, I buried it. Here it is. Okay, so let's take a look. Now, so far, here's what we've done so far, and I hate the fact that everything's choppy. It's not my fault it's choppy, it's just what happened, okay? We went over how to classify and balance equations, is that correct? So if I were to give a quiz on that, you would be okay on that, wouldn't it? Not today.
Hint, hint.
Wait a minute. You okay on that? So you'd be able to do that, right? And we did that, and we had some little tricks on balancing equations. We did that. And then we even had your favorite, where you take the word equation and turn it into Chemonese, right? Take English and turn it into Chemonese. We did that. Okay, now, the next thing we're going to do is, now that you have mole concept out of the way, you could convert anything into anything. If I said 20 grams of sodium equals how many atoms, couldn't we do that with factor label? If I said, how many moles of ions are in 20 grams of sodium nitrate? Oh, you know what? I forgot something. Here. I think this is you, Marie. We forgot something here. It's 2 moles of ammonium ions and 1 mole of carbonate ions, but also how many total moles of any kind of ion?
3.
Yeah, 3 moles of any kind of ion. Did I get that? That's why I forgot that that's part of the example too. So now, this is something that I want you to be so good at this that when you go to college and people around you say, I think I remember how to do that, you're going to teach them, because they're going to not remember everything. All right? And so you're going to be their teacher. So let's take a look at this from here. This is actually a real experiment that this is a real chemical reaction that takes place in space. If you were in a space station, just not. Yeah. All right. So here it is. It says solid lithium hydroxide, and go ahead and read that and see if you could fill in the balanced equation. Let's see if we can do that. Can you take the English and turn it into Chemonese? All right, let's try it. If you're sitting next to somebody, work together. Work together. All right? Let's do it. Solid sodium hydroxide is used in space vehicles to remove carbon dioxide from the environment by forming solid lithium carbonate and liquid water. Okay, let's do that.
What we got this? Well, where's your sheet? Get your sheet.
You need to find it. If not, I can make another one. But
Was this a new package or was this from?
Lithium grams and hydroxide grams.
Oh, I think I had this.
Oh my gosh, yeah. Thank you. Didn't even look.
all right, now we've taken about. All right,
Oh my gosh, it's the first one.
Oh my god.
Yeah, look.
all right. Ready? Who wants to start? Mason, help me out. What do you start with? Lithium. I know.
Well,
It's just lithium?
hydroxide, so there's gonna be an OH too.
Wait, lithium OH2, how do you know that? Why'd you say lithium OH2?
I didn't.
Oh, okay.
Just lithium OH, right?
Okay, LiOE, is that right?
Yes.
Okay, and then, it's gonna react with carbon dioxide, what's it gonna form?
Oh, I see, I see, I see.
What's one of the products gonna be?
Well, you have,
You got
it's gonna be lithium or no, you're gonna need the carbon.
it. Never seen done.
Alright, lithium carbonate, how do you write that?
I didn't really know.
How do you write lithium carbonate?
Carbon is a -4, so you're gonna need 4 lithiums.
Hang on,
Oh, it's carbonate.
yeah.
So it's always 3.
It says lithium carbonate here, see that?
But it's not balanced. It's not
Wait,
balanced.
let's get our formulas right before we balance it.
Well, it's not balanced.
Is lithium carbonate the right formula?
Well, hello Caldwell, this is Mr. Holland, and
Oh.
as has become tradition, we want to close our Friday in prayer. As we acknowledge the Lord for good provision to each of us. I'm going to share hopefully what has become a familiar passage of scripture with you this year. Galatians chapter 5:13, which has been our theme, which reads, For you were called to freedom, brothers, only do not use your freedom as an opportunity for the flesh, but through love serve one another. But in verse 14 it goes on to say, For the whole law is fulfilled in one word, you shall love your neighbor as yourself. For the dialectic students, this should be another good reminder of what we talked about in chapel on Wednesday, about right responses and how we choose to serve others, even when it's not convenient, and even when it may not be expected of us. So as we go out this weekend and invite some colder temperatures in, for those of you that will be going to Westchester and competing tonight, I wish you well, and I challenge you to demonstrate not only who we are as Caldwell families and the community, but who the Lord calls us to be. Let's pray. Heavenly Father, we thank you again for another week to learn and grow here at Caldwell. We thank you for the freedom that we have to serve you, to be so open about our faith and our relationship that we have with you. Lord, as we go into the weekend, we just thank you for your continued provision. We thank you for everything that you do for us and the ways that you go before us. Lord, we ask for safety for those that will be traveling and playing tonight, for those that will be playing the Powder Puff game tomorrow evening, for those that may be traveling this weekend, Lord, we ask for a time of rest with families. We ask that you bring us back safely again next week, Lord. We ask all this in your name, amen. Thanks, everybody.
Well, thank you, that's very nice.
Can you get out now?
No, 2 o'clock. Hey, okay, let's finish this, and then, how do you write lithium carbonate?
Well, I believe carbonate is it's a 2er.
-2? Uh-huh.
Yeah.
What about
So you're gonna
lithium?
need 2 lithiums because it's in 1.
Okay, all right, very good. And then what else? And we have water, right? Now, after we're sure the formulas are right, now we balance it, right? Any little tricks you see? I noticed that carbonate is not carbonate over here, so it's might be a little tricky. We have to be
You can
careful.
always write H2O as HOH.
That might help. And I said sometimes it helps. And when do you do that? Not always. It's when you see hydroxide on one side and water on the other. Sometimes it helps. Let's try it.
So you have 2 hydrogens on the right, so you need 2 in the left. So
Okay, wait now. On the right, you have 2 hydrogens.
I'll jump in back.
Now I also have 1 hydrogen though. Oh, I see. In this case, so all the hydrogens are in hydroxide, aren't they?
Yeah.
So we have 2 hydrogens. You want to put 2 here?
Yeah.
That gives you 2 lithiums, and doesn't
Yeah,
it?
which is already on the other side.
But that gives you 2 oxygens. But how many more oxygens?
There's 2 right there, so
So 2 oxygens plus 2 more is what?
4. And we have 4 on the other side.
Ooh, now carbon's the only thing you have to check. What about carbon?
You need
We did? Did that work? Did that work? All right. So is it balanced now? Okay, so what I'm going to do, this is what I want you to work on a little bit, all right? I know you've been out of school for a while. But I am gonna make you do the factor label first, and then we'll do the shortcut. Remember in 10th grade I showed you shortcut? And once I showed you shortcut, you didn't want to go back to the long cut. But what happens with shortcuts is if you forget the shortcut, you have nowhere to go. But if you rely back on factor label, it doesn't matter if you take chemistry next year, 2 years from now, 3 years from now, it'll come back to you. All right, so let's do a little bit here. How many moles? Oh, what else is given here?
Yes.
What mass of carbon dioxide? We're going to do all these, but we're going to start with 1,000 grams of lithium carbonate, lithium hydroxide. Okay. Now, what I would do is before I just start stoichiometry, I would make myself a little list over here. Let's do some molar masses. What's the molar mass of CO2? That's kind of a famous one. You use that a lot in chemistry. Anybody know the molar mass? What's the molar mass of CO2? And what does that mean, molar mass?
What mole of it would weigh?
Right, how many grams it takes to make a mole, right? Grams per mole. Now, what's the molar mass for water? That's an easy one. What's the molar mass for water? I need to work hard. We've been out for a long time, okay? 18 grams. Now here's some hard ones. What's the molar mass of lithium hydroxide? What's that? 7 plus 8 plus 1, 8. 8 plus, what's oxygen?
16.
8 plus 16 is what? What is it? 24. Okay, and one more. Lithium carbonate. All right. Lithium 7, 2 times 7 is 14. 14 plus 12. 26. And this is 48, isn't it? 3 times 16? What did I say, 26 and 48? Is that what I said?
Yeah.
74, is that right? Okay, now they have molar masses. Here's what I'd like you to do, okay? Now, I understand you've been out of school for a while. I'd like you this weekend sometime say, could I do these? And I'd like you to come back on Monday and say, I think I got this down. So let's try the first one. How many moles of lithium hydroxide? I don't have 3 minutes. So what do we start out? What's our given?
Very good.
Okay, now here we go. This is the key to factor label. Whether you do it next year, 2 years from now, whatever. What label has to go away right now?
Grams.
Grams of lithium hydroxide.
That.
What would you like to replace it with? Moles. Okay, now, what is the mole equivalent for lithium hydroxide? 1 mole of lithium hydroxide equals 6.02 times 10 to the 23rd formula units. I'm not going to use that today, am I? Equals what? Equals what? 24 grams. Okay, now look what happens. And I think we're done, and we have moles of lithium hydroxide. Now what I'd like you to do this weekend, all right, I'll stop here. I would like you to take this home and say, I could sit here, I'd like to sit 20 minutes. That's all I'm asking for. 20 minutes of your time, and come back on Monday and said, I've done this. And a lot of things came back to me, or this didn't come back to me. All right, you have a nice weekend.
Thank you.
I'm glad to see you. I love seeing you again. I missed you. One day I thought you were coming and you weren't here. So I said, what?